Hello and welcome to Stars, Cells, and God. This is the show where we discuss new discoveries taking place at the frontiers of science. These are discoveries that have theological and philosophical implications, and discoveries that point to the evidence of God's existence. My name is Jeff Zweerink. I'll be your host today. We'll be joined with Hugh in studio talking about some James Webb Space Telescope data and discussion. But before we get into that discussion, I want to encourage you to subscribe to our channel, Reasons to Believe. Click on that bell icon so you can be informed of our new videos. Learn more about us at reasons.org or by following us on social media at RTB_official. Let's get started. Hugh, good to have you in studio today. I'm going to just throw the floor over to you. I know you've got some James Webb Space Telescope stuff that you want to discuss, so why don't you open us up here?
Right, and I want to just talk about how there's been a partnership between the Hubble Space Telescope and the James Webb Space Telescope. So it's good that the Hubble is still up and running. But a lot of what astronomers have been doing is looking at the intriguing discoveries made by the Hubble Space Telescope and using the James Webb to dig down deeper and see if they can make some more significant discoveries. So the first slide I got here basically shows you the James Webb Space Telescope. I actually got to see it being constructed because it was built here in Southern California. And so quite an amazing project, but you can see here that it's got a sun shield basically to make sure that it's really pitch black when they're making the observations.
And to give a sense of scale on that, I think that sun shield's about the size of a tennis court. So this is a very large instrument.
It's a very large instrument. And the next slide just shows you how much bigger the James Webb Space Telescope is than the Hubble Space Telescope. But also shows you how much technology has advanced since the Hubble went up, because the James Webb Space Telescope only weighs half of what the Hubble Space Telescope weighed.
Right.
And moreover, they were able to fold it all up inside the cone of a rocket that was sent up, an Ariane rocket. So the fact that they were able to compactify it all into a tiny volume, send it out 1 million miles away, and then have it unfold in just the right way so that it had this immense telescope sitting there. Really quite a remarkable achievement.
Just the technology and engineering behind this telescope is remarkable, regardless of the scientific output it gives. It's a really impressive instrument.
It is, and the fact that it's situated 1 million miles away, it's like you're not going to be able to send a repair mission up there.
Nope.
So that meant there can't be a single engineering error. And so that's why they took 10 years to basically put it together, because they knew it had to work perfectly. There couldn't be any glitches. It had to unfold just the right way.
Right.
So it's like they were being very concerned, let's not waste the taxpayers' money, although it did cost a little bit more because of all the care they went to.
Well, I mean, two of the things that impressed me about the technology is, one, that this is an optical quality mirror that folds and unfolds. I mean, you've got to be at the nanometer scale smooth on that, and that's really impressive. The other part that has impressed me, go back to the sun shield, is that the difference in temperature between those two sides is something on the order of about 300 Kelvin.
That's
so
right.
It's really impressive just that all worked out in the emptiness of space.
Yeah, you want the receiver to be close to absolute zero, because that's where you get the greatest sensitivity. So that's the purpose of the sun shield there. And you notice it's got 5 layers, because they're aware micrometeorites can make holes in it.
Right.
So if they got 5 layers, they think, hey, this is probably going to be good for about 30 years before it begins to degrade the image.
Right.
But consequently, astronomers are being fairly aggressive at making sure they use this telescope as efficiently as possible. And because it's 1 million miles away, they don't lose any observing time.
Right.
People aren't aware, like with the Hubble Space Telescope, you lose about an hour a day. With James Webb, you don't lose any time at all.
Well, specifically, it's positioned, if I remember correctly, if you take the Earth or the Sun, Earth, it's situated on the opposite side of the Earth from the Sun, so it's always facing away from the Sun, whereas the Hubble's orbiting around the Earth in such a way that it points at the Sun occasionally. So.
It does, right. So it's a way to get more astronomy done.
Right.
And now there's a second major telescope that's right there at that Lagrange point, a million miles from Earth, that's basically surveying galaxy clusters. So it wouldn't surprise me if we see a number of telescopes being positioned at that location.
Right.
But what the Hubble Space Telescope did in the last few years was try to do really deep images, in other words, long exposure images of the distant universe, trying to do what they could to explore what's called the cosmic dawn, which refers to the first billion years of cosmic history. And so people were aware it's going to take a while for the James Webb to get up and running. So Hubble was actually said, let's do the best we can with Hubble to actually get some insights into the cosmic dawn. And Hubble identified a number of very distant, very bright galaxies. And so these were targeted as the things, hey, James Webb, let's go and focus on this.
Right.
So, and we've
Well, so is just for clarification, is the Hubble just incapable of observing out there because it's too small, or is it a problem of the Hubble is largely optical and ultraviolet, and the James Webb is infrared, so the red shifting shifts it more
It's
out
both.
of Hubble's range? So
I mean, the James Webb is a much bigger collecting area, so it's able to observe at much dimmer magnitudes than what the Hubble is able to do. But also, James Webb on purpose is an infrared telescope.
right.
Now, there was an infrared spectroscope on the Hubble, so they were using it to try to get the red shifted images, because yeah, you're right. If you're looking at the very distant universe, optical wavelengths get shifted into the infrared. So, but James Webb was designed specifically to get very sensitive infrared images. And there's actually two different infrared spectroscopes on the James Webb Space Telescope. So it's able to dig into the infrared
Right.
to a far deeper degree than was possible with Hubble. But it's like Hubble already gave them kind of an advantage. Here are some bright galaxies we
Right.
found in the cosmic dawn. And so they became kind of the first targets. And Hubble basically found these through very deep exposures. And I keep telling lay people the really deep James Webb exposures are coming.
Right.
We don't have them yet. I think the deepest exposure so far has been at 30 hours, whereas we had one with a Hubble that was 2 whole weeks.
Right. Yeah.
So, but James Webb is going to do those, but it's like, hey, that's a huge investment of telescope time. Let's see what we can do with the shorter exposures.
Well, and what's impressive about the James Webb is that it gets similar sort of galaxy or object numbers with that 10, 12 hours exposures that it took Hubble 10, 12 days to get. So
Correct.
It really is an impressive instrument.
Yeah. Well, I got the next image basically shows you this is one of the longer exposures by the James Webb Space Telescope. And there are a few stars in the image. You can tell them because you can see the spikes of the diffraction patterns of the stars. But you notice you can count the stars basically on one hand. Everything else is a galaxy. And this image shows you 50,000 galaxies. So it's just revealing just how many galaxies are showing up in the early universe. Some of these galaxies, of course, are closer to us and therefore are not that far back in time. But most of the galaxies here, we're looking like in the first 4 billion years of cosmic history, many of them the first billion. And the next slide shows you the target. Okay, that galaxy called GN-Z11. Z11 basically refers to the redshift, which basically tells you that you're looking at a galaxy that's just 400 million years after the cosmic creation event.
So this is pretty early in the universe's history then, as far as galaxies go.
The Hubble tried to determine just exactly how distant this galaxy was, and it was such that it was 350 million years after the cosmic creation event. And the galaxy looked awfully bright to be that early in the universe. And so one of the objectives of James Webb, can we get a better distance measure? And it did. It's 410 million years after the cosmic creation event.
That's pretty close to what Hubble was getting there.
Pretty
a
close to
little
what
bit
Hubble
later,
was getting.
But,
But the fact that it's a little bit later basically removes some angst on the part of astronomers.
Okay.
Because that meant that there's a little more time to get that galaxy as big and as bright as what they found. They're also able to measure the size of the galaxy because what we got with Hubble was an approximate size. And so what we got with James Webb was a much more accurate picture of its size. But the basis of this paper is they saw something that Hubble didn't see, which was a huge, dense cloud in the halo of the galaxy. That didn't show up in the Hubble Space Telescope image, but they found it in the James Webb image. And it was bright because it was being illuminated by the stars in the core of the galaxy.
Okay.
So evidently those stars had to be fairly numerous and bright enough to illuminate that cloud. But the fact that the cloud was illuminated meant that the astronomers could use one of the infrared spectroscopes on the telescope to actually measure the chemical composition of that cloud in the halo of the galaxy. And what kind of made the paper breakthrough, it's the first time astronomers have ever seen anything in the universe that was only hydrogen and helium.
So when they looked at the cloud, they could see clearly enough to see where the spectral lines were and they weren't.
Right.
And all they found were spectral lines from hydrogen and helium.
And those lines were bright, and they looked for lines of other elements.
Right.
And couldn't find any. So they said, we think we've finally found a pristine gas cloud in the universe. And what they mean by that is a gas cloud that exists before any stars form.
Right.
And so we have a cloud here. There's no stars in it, but it's sufficiently illuminated that they could determine the composition of the cloud. And it's exactly what the Big Bang would predict.
Right, okay.
That before stars exist, the only elements you're going to have is a hydrogen and helium and a trace amount of lithium. But we're really talking a very, very tiny trace of lithium. I mean, we're looking at 24, I think, I got the numbers down here somewhere, 24.67% helium, and then you got 75.33% hydrogen. That adds up to 100%.
Yeah. So it does match the expected hydrogen to helium mix too. It's not just that it's only hydrogen and helium.
Well, that's it.
It matches the expected abundance in Big Bang cosmology.
The maps that we have of the radiation left over from the cosmic creation event, what astronomers call the cosmic background radiation, those studies by the Planck satellite and the WMAP satellite actually reveal the primordial hydrogen abundance and the primordial helium abundance. And yes, it matches what we'd expect of the universe before any stars form at all. But the fact that this cloud was illuminated so brightly actually gives us some information about the stars and the core of the galaxy, basically saying that the luminosity has to be equivalent to about 20 trillion times the luminosity you expect from the sun.
So 20 trillion times the solar luminosity, which either means there's 20 trillion stars like the sun, or a number of stars much, much brighter than the sun.
Yes, and of course it's the latter.
Right.
Because we're looking at a small galaxy, and they determined that the galaxies, or the stars in the core of this galaxy, to add up to that minimum luminosity, must be stars that fall between 50 and 1,000 times the mass of our star, the sun.
Okay.
Where most of them are in the high end, in the hundreds and close to 1,000. A few might be down around 50 or 80, but the majority would be 200, 300, 400, 500, 800 times the mass of our star, the sun.
So if you're comparing just for luminosity purposes, so you got our sun, mass of one solar mass. If you go up to 100 solar mass star, how much brighter would that be than our sun? Or
well,
would we
the
expect?
luminosity of a star goes up with a 3.9 power of the mass.
So almost 4 times. So,
Almost
so
four
if you're
times.
100 times larger, you're 100 million, no, sorry, 10 to the 8, 10,
Yeah, 100 million times
100 million
brighter.
times brighter. Okay. So,
Yeah.
so that's why you can get up to that trillion. It doesn't take a lot of those stars
All you
to get
need
up
is
to
a few
trillion.
thousand stars
Gotcha,
at
okay.
that mass to get up to 20 trillion.
Right.
So, but this answers a major question. One of the reasons why we wanted the James Webb Space Telescope, we wanted to know, what are the first stars like? Are they very massive? So there's a big debate. The debate is still flourishing in the scientific literature. Are they predominantly very massive stars? Do they have a range? And, we do see, even in our own galaxy, polluted first-generation stars that are not very massive. They're the ones that last long enough that we can actually see them.
Yep.
Whereas the really big ones burn up quickly and they're gone.
Yeah.
So, but this is an opportunity to actually see those first stars because the galaxy exists just 410 million years after the cosmic creation event. I mean, we astronomers think that the initiation of star formation probably begins when the universe is about 200 million years old. We're trying to nail down that number, but that means that star formation at most has only been going on for about 200 million years in this galaxy. But that means that the massive stars, a number of them are still burning. So, but that's been one of the goals, as the different Big Bang creation models predict that the first stars will have different mass ranges. This discovery indicates that it's most likely in the high end of the mass range, not the medium or the low end.
Well, and presumably, say it started 200 million years after the Big Bang, where stars started to form. These stars wouldn't have formed then because they would have burned out well within a couple 100 million years. So these would have been stars that were still forming. I guess we don't know what the composition of the stars are, but it does say that there's still gas clouds floating around in these environments that haven't had star formation happen yet.
They do know that star formation is very aggressively happening in this galaxy because we have these very massive stars. The stars have to be very massive to explain the luminosity, which means the stars are forming right now. Well, when I say right now,
yes,
at the look-back time.
Shortly before we're getting the light from this image. So.
Right. So, and that also helps resolve another problem because astronomers have been seeing in these very early galaxies supermassive black holes. Not many, but we are seeing some. And a supermassive black hole is 1 million times the mass of our star, the sun. And so the challenge has been, how do you get a black hole that massive, that early in the universe? Well, what these astronomers are finding out, hey, if the stars are coming in at 500 to 900 times the mass of our star, the sun, it's going to be relatively straightforward to get a black hole at that high mass range of 1 million times the sun. And it actually contributes to the luminosity of the galaxy. So some of the luminosity is from the newly formed very massive stars. Some of it is from the supermassive black hole that's in that galaxy. And I think I got an image here of what a supermassive black hole looks like. This is one from the M87. It actually weighs a little more than 6 billion times the mass of our star, the sun. But actually,
I thought it was closer to 1 trillion, if I remember. Has the numbers changed on that? I always thought this one was one that was right at around 1 trillion, but I may be remembering a different.
It's about 6 2/3 billion times.
That's still a lot. Yeah,
it's still
okay.
A lot,
So only 2/3 of a billion, as opposed to or 2/3 of a trillion instead of 1 trillion. So
this is by the Event Horizon Telescope, and basically shows you, if you get towards the black hole, it's black. That's a little
see
donut
the shadow
hole,
there.
because that's where material is getting sucked into the black hole. But eventually, when you reach a certain proximity to the black hole, even light can't escape.
Right.
So it's black. But as material is being sucked into the black hole, outside that event horizon, it's being very efficiently converted into energy. And with an efficiency that's as much as 600 times more efficient than what our sun's nuclear furnace does.
Yeah.
So that explains why these are the brightest objects in the universe. They're converting matter to energy between 10 and 42% efficiency. So that's that bright ring you see around the black hole. And so in this galaxy GNZ-11, they're seeing luminosity from these very, very bright stars, highly massive stars, plus a supermassive black hole. And, so this whole idea that, hey, we're going to have to make adjustments in our Big Bang creation models, well, not if we realize the firstborn stars are predominantly very massive and that you actually can get supermassive black holes early in the universe.
So I find this cool, fascinating astronomy. So from an apologetics value, how does this help the Christian who wants to say, hey, this is what science reveals, or how we see God in science?
Well, we've been writing for decades now that the Big Bang creation model, some of its fundamental components were predicted in the Bible thousands of years ago.
Okay.
Astronomers, recognize the universe had Big Bang features starting in the 1920s, but thousands of years ago, the Bible laid this out. Like the universe has a beginning. It's a beginning that includes the beginning of space and time. The universe it has constant laws of physics.
Right.
One of those laws is a pervasive law of decay, which means that the universe will indeed get cooler and cooler as it gets older and older. And when you dig down into the astrophysics of it all, if the universe indeed starts infinitesimally small, you're going to have a universe that starts off with only one element, hydrogen. And then as the universe cools, in the first few minutes after the cosmic creation event, some of that hydrogen gets fused into helium. All the other elements are made by the stars, which means according to the biblically predicted Big Bang creation model, you should be able to see in an early epoch of the universe only hydrogen and helium and nothing else. This is the first time astronomers have been able to document that through observations and not just their theory. So we've directly observed a gas cloud that's free of any elements except hydrogen and helium. Astronomers are excited to look for more bright galaxies, see if they can find more gas clouds on the halo, and see if we can confirm this. And also go back to this galaxy and say, let's do a really deep spectroscopic observation and see if we can really show. Maybe we can even pick up that tiny amount of lithium, because this spectroscope wasn't quite sense enough to do that.
Right.
But it did indeed confirm, hey, no carbon. Because when you look, even when you get the first star, you get carbon being produced quite quickly. So the fact that this is carbon-free and oxygen-free, this stands as a major confirmation of the Big Bang creation model.
That is kind of a remarkable thing, just going back to the science a little bit, that given how pervasive hydrogen and helium are, that though you can find hydrogen and helium everywhere, it's hard to find an object that only has hydrogen and helium, that so efficiently has star formation and other things, distributed elements throughout the universe, that it's been really hard to find something like that. And now, after hundreds of years of telescope formation, we finally can do that. That's a pretty remarkable thing.
Well, it is remarkable because there was a lot of doubt that the James Webb would be powerful enough even to pull us off. Because if you're going to find an object with only hydrogen and helium, it's got to be before stars form.
Right.
Because it doesn't take a very big star to pollute the rest of interstellar space with the ashes of its nuclear burning. So the fact that this was done is like, wow, we didn't know James Webb could do it. It really can.
So stars make a pretty good leaven for any sort of stuff beyond hydrogen and helium in the universe.
Oh, the rationale for why this was possible, they used stars to find a gas cloud where no stars had formed.
I know, that is cool.
Yeah, so it's a
little bit ironic almost.
It was quite an achievement to actually use a bunch of stars to actually find a cloud where there were no stars.
Very good. Any final comments? Or
no, that'll do it. Thank you.
Well, very good. No, I appreciate that the discussion there, Hugh. And I kind of want to take a discussion that's related to that because as the James Webb, as you've described the technology behind it when it started observing, and we've probably talked on this show at least a couple of times about this, where as they started observing galaxies in the early part of the universe, they're finding galaxies that are far more complex and larger than what they expected. And so, Eric Lerner, I remember, used this as an impetus to say, oh, Big Bang cosmology is wrong and we need to go a different way. But I don't think that's the right approach to things. But it does raise this question of, so we've got our Big Bang models out there. We think those are correct. Nothing about finding these galaxies says Big Bang cosmology is not correct. But it does raise the question, how do you get these very advanced galaxies in such a short period of time? And so, as you've illuminated, not only is it large galaxies, but you get very large supermassive black holes. There are some other features that have arisen that now we can see what it looks like, as opposed to just extrapolating or interpolating between the beginning and what our telescopes like the Hubble were revealing.
And the real test of the Big Bang model is the distribution of the galaxies. How many are big and bright? How many are tiny and faint? And that's why I said we're going to have to wait for the really deep James Webb observations, because what we're really picking up are the easy ones to detect.
But even at that, if you're getting really large galaxies forming in a time scale where they can't form, that poses a problem. Or what it says is that our Big Bang model is not complete, that we need more details in it. And that's kind of been what I've argued all along. But what I thought was interesting is there's a paper that has been making the rounds in some of the popular press arguing that actually it's not that the James Webb are finding galaxies that have formed too rapidly. It's that our measurement of the age of the universe is wrong. And this is the sort, it makes it sound like this is just this is a new thing and we're kind of radically going different. And in reality, what's always gone along here is that when you see something new that it's like, okay, we don't quite know how to explain that, you start looking for what are the explanations. And there's generally, is a little bit of a generalization, but there are kind of two groups of or ways to approach that. One is saying, all right, general Big Bang cosmology is correct. We don't understand galaxy formation, or we don't understand this process, or how white dwarfs cool, or it's like the details are where we're missing. But then there's a larger class that says, okay, maybe we're missing something about the large-scale physics of the universe, that maybe general relativity isn't quite as accurate as we thought, maybe light doesn't behave quite the way we thought, things like that. And this particular paper, the one that argues that the universe is not 14 billion years old, like Big Bang conventional lambda CDM Big Bang cosmology would say, they're saying, wait a second, if light and the universe and our laws of physics behave a little differently, the universe could be much older. And a large part of the motivation for looking at this was the idea was this recognition that there are these large complex galaxies that were troubling or difficult to explain in our standard model. And so what they're saying is, here's a way of looking at the universe where, yes, it's a Big Bang universe, but the age is much larger than what we thought. And why I find it interesting is because, you've got Big Bang cosmology, and then you've got this troubling new galaxies. How do we explain them? This model says, all right, well, we can explain the new galaxies, but it makes the Big Bang a little bit more complicated. And I think how it makes it more complicated is what's interesting about this discussion, because the first thing they say is that back when we first started measuring redshifts, and here's the copy of the paper. Just it's testing CCC plus TL cosmology. Cool terminology and acronyms there. That TL stands for tired light, because when they started noticing that we've got hydrogen in a distant galaxy or whatever the element was, but it's the where the wavelengths was shifted to the red end of the spectrum. Question is, how do you explain that? Well, in Big Bang cosmology, you explain it dominantly or almost entirely by the universe is expanding, and so it stretches the photon paths as it's coming across the universe,
Doppler effect.
and that redshifts it. there was another idea put out by Fritz Zwicky in I think it was 1928 or 29, that as light travels across space, it actually loses energy.
I actually heard Fritz speak about this at Caltech.
All right, very good.
How he came up with the idea, and he said, I also refuted it.
Well, and to Fritz, or to Zwicky's credit, it's like, here's what it is, here's how it would work, and if it worked, this is what you would measure. So this wasn't like, oh, let's just throw an idea out there. He really did a lot of work to investigate, or to outline how you would investigate it and see whether it's there. And I think it's worth just kind of stepping through a couple of the reasons why scientists don't think this is correct. To me, the biggest one is, okay, so you got to provide a mechanism by which the light is losing energy.
How does it get tired?
In the expansion of the universe is what's stretching out the wavelengths. So you've got the physical mechanism there. What they recognize is, typically the way you can lose energy is through interactions with other particles. And so you could imagine scattering through a gas. That will lose energy in doing that. But in doing that, that will also blur things out. And so they could look at how blurry were things, and lo and behold, they could show that the blurriness that was expected if scattering was the mechanism didn't actually exist. And so, okay, so that's not it. But then you can just say, all right, let's say we don't even have a mechanism. Let's just say the light does lose energy by some unknown mechanism. That has consequences for the things that we could measure. For, among other things, you mentioned the cosmic microwave background radiation, that by and large, it's a very good black body spectrum.
Right.
And so black body spectrum gives the temperature of the black body, and so we can make measurements of that. Well, if the light, as it's coming from these distant objects to us, is just losing light, that it will change the shape of that spectrum, because a black body spectrum where the universe is expanding has a predictable shape to it, whereas if the universe is not expanding but the light is getting tired or losing energy, it's going to shift the spectrum of that, and lo and behold, that doesn't show up.
Right.
Furthermore, when you go look at the supernova that go off, type 1a supernova, they have a characteristic light curve to them. They brighten and then they diminish in a certain time scale. Well, in supernova or in Big Bang or in standard Big Bang cosmology, because the universe is expanding, that time gets dilated.
Right.
That's not going to happen in a tired light scenario, and so we see this time dilation happening, correlating with redshift.
And we see it with distant quasars as well. It's not just
exactly.
With a supernova.
Yeah, no, it's not just one. But it's kind of the point I'm getting at is that there are multiple lines of evidence that people have looked at and said, okay, does tired light work? In fact, connection with one of your friends, Alan Sandage. Another one is you look at the surface brightnesses of galaxies, and again, in an expanding universe, the galaxy is getting smaller and redshifting, whereas in a tired light scenario, it's not getting smaller, but the light is losing energy. And so again, it has a very different signature than what we actually observe. And again, the Big Bang cosmology signature is what shows up there. So there's a lot of data, a lot of observations, and a lot of research that shows, okay, tired light doesn't really work well. So the idea that we're bringing in a tired light scenario kind of shows how far out this model is at some level. But it's not just okay, so we're introducing tired light again. If I understand what the paper's saying, it's more or less saying, okay, we've got Big Bang cosmology of some sort. So this is not a not Big Bang model, which is what the tired light was trying to originally get around, if you will.
Right.
This is, okay, so what happens if you've got a model where light loses energy as it propagates through space, and to explain to account for all the other observations that say just, no, the universe isn't expanding, you also have to have, the author puts in this idea of covariant coupling constants. So now you have to have the speed of light and the gravitational coupling constant and the Planck's constant all varying. And you can do calculations that show that if they're going to vary in a predictable way. So once you measure one, the other ones are going to vary the same way. So unless you account for that fact, you're not going to measure that they're actually varying. And so all that to say is he puts together these covariant coupling constants and tired light and says, what I can do in this model is look at the baryon acoustic oscillations, which are one of the more powerful, potent evidences for Big Bang cosmology, or the standard lambda CDM Big Bang cosmology. I don't want to make that specific distinction because it's now got this dark energy and dark matter. Lambda's the dark energy, CDM is the dark matter, is our standard Big Bang model. He's saying that explains the baryon acoustic oscillations, which effectively says there's this preferred size which things cluster in the universe. And so he's asking the question, can my model explain that? And he goes through a lot of calculations and show that, lo and behold, yes, it can explain that. And it does it where the baryon density is 100%. So it does it without need for dark matter, which is kind of an interesting phenomenon. That's a cool way of doing that. And so it's not just that he's saying, well, here's a way of explaining how we can get an older universe where we can have these galaxies form, but he's now saying, does this actually explain the other things that we use to point to our standard Big Bang model, and can it explain those? And he says, okay, I can do that with the baryon acoustic oscillations, but what he does say at the end of the paper, in fairness, it remains to be seen if this new model is consistent with the CMB power spectrum. So not just how the sizes and scales of the cosmic microwave background ripples, and the Big Bang nucleosynthesis of light elements, the lithium, beryllium, the light deuterium there. So there's still a lot of work to do that, but nonetheless, he's saying I've got a model, at least to the extent it's been investigated, does account for the big features that I've looked at, and it has a universe that's much older, which now makes these large galaxies not so problematic.
And by much older, we're talking almost double the age.
It is almost double the age.
Yeah.
Again, this is still Big Bang model, so none of this would say, well, this is, doesn't match what biblical, or it doesn't go against the term, the biblical creation model you have, because it would still be a Big Bang model.
But he is fiddling with the constants of physics.
He is.
Yeah.
And, this is a question, part of what I not wrestle with, but kind of think is interesting in there. It's like there's wrestling with the constants of physics, but in such a way that the universe still behaves reliably, which I would argue is really what Scripture is saying, that the universe behaves reliably, regularly, and orderly. So this would still be in that class, but nonetheless, it's a very different picture. And why I think this is all interesting is that there's a lot of times where there are very dogmatic statements made about, oh, this is the right way. I think standard Big Bang cosmology with dark energy, dark matter, Hubble constant around, high 60s, low 70s, that our picture is correct. That's a very good picture and it explains a whole lot of what's out there. It doesn't mean that that's the only way you can explain all the data that's there. And why I think that's interesting is that we talk a lot about multiverse scenarios, and often the multiverse is used to explain why life shows up. Life is clearly acknowledged as being very rare. It's an extraordinary phenomenon in the universe. And so you say, well, the multiverse explains why life shows up. Yes, it's very rare, but it's got to happen somewhere. Well, if that's the kind of reasoning we're going to use, there is absolutely no way you can rule out this being a legitimate explanation for why we're here. Because I think it's probably it's a bizarre way of looking at the universe at some level. But if it can account for all the data we have, and the multiverse means that everything that can happen does happen, what do you do with that?
The Bonbon modified Newtonian dynamics.
Yeah, this is a variant of that. So.
Yeah. It explains some of the data, but not all of the data. And so in this case, it's explaining, okay, how do we get these bright galaxies early? Mm-hmm. This is an alternate way of doing it. And I do appreciate that the author said, this is an alternate way. There are other ways to explain these galaxies without making the universe double the age.
Right.
So he's being honest there. But there's a whole lot of data, just like what that Mon can't explain, this can't explain either. It's like, how come we don't see any objects in the universe older than about 13.5 billion years? I mean, if the universe really is 26 billion years old, we should see some stars that are older than 13 billion years. and we don't.
Well, but I'm not so sure that so this is, I don't know, I haven't pressed in hard enough into his model to know how to explain that. And maybe that's something he's not investigated or whatever. But I do think some of that would be, at some level, you got to go and say, we're so used to thinking about it in these terms, and so these are the sorts of results we get. What he does say in the model is that you have to be very careful that you're consistent all the way through here, that your bookkeeping and accounting is really important. Because I don't get to say, well, if our lambda CDM, this is the sorts of measurements we're making or these are the results we're getting, you can't explain it, therefore your model's wrong. I have to say, okay, the actual measurements where I see redshifts, I see spectral lines, I see this. Now, how do I explain that in this model, or can it be explained in that model? And it's taken us a long time to do that in our standard cosmological model. It wouldn't surprise me, or I'm at least willing to say, okay, give them time to explore that, because I have seen enough places where people say, well, Mond can't explain this, and then they go in and they wrestle through, and lo and behold, it can give an explanation for that. Now, I still think the conventional cosmology is a better way to look at it, but there is a little bit of inequitable distribution of power. There's a lot of people working on the standard Big Bang model. There's not so many people working on this. So I'm willing to give people a little bit of the benefit of the doubt there, but it's a great point you raise. You have to be able to explain all the data, not just some, or a significantly larger fraction of the data than what Big Bang cosmology
I remember, back in the days when Fritz Zwicky was proposing this tired light, it's like there was a time back in the 1960s where really the only tool we had for measuring the age of the universe was the Doppler effect. Galaxies farther away are moving farther away. And so they said, tired light might be an alternative to the Doppler effect, in which case we're wrong about the age of the universe. Things are different today. We got multiple independent tools for measuring the age of the universe. I mean, we got the decay of radioisotopes. We got the cooling curves of white dwarfs. And, we can actually measure the ages of stars by the chemicals or the elements that exist in those stars. So it's a little bit different than the 1960s, where the predominant method for measuring the age of the universe was the redshift.
No, that is true. But, and again, just to defend the position being put forth here, and this is why I think it's important to recognize, he is arguing that these fundamental constants are also changing. So if the speed of light's changing and gravitational constant and Planck's constant, that's going to affect the ages we're going to get through radioactive decay and.
Right.
And so, there's a part of this where I look at this and say, this is just what scientists love about science. How can I go about explaining this? And is there a way of testing this to see whether it works?
In reading the paper, I didn't notice he was appealing to a change in the velocity of light.
Right.
But we can measure that out to 13.5 billion light years, and we see no change.
But what he's saying is you can't just say, is the speed of light changing with all this other stuff being constant? You have to also take into account what would be the measurement if the speed of light is changing and gravitational constant is changing and Planck's constant is changing. So it is a little bit more sophisticated model in that. And so I don't know. I don't have an answer of whether it works or it doesn't. But I think what I found interesting in this is that, one, there are always multiple models you can propose to explain all the data that's out there. I think this is going to become increasingly important as more and more people look at the multiverse as an explanation for how life got here. The implications of the reasoning behind that is that anything that explains the data is going to happen somewhere. How do we know that's not our explanation here? And I think that's going to be very detrimental to science if we're not really careful.
I understand all this, but again, it's kind of deja vu to me, because I remember when I was a grad student, there were people saying, these quasars we discovered, it doesn't fit the Big Bang model. They're way too bright. There's too many of them. And so that's when they were invoking all this, let's introduce quasi-steady state model. Maybe that'll explain it.
Right.
Let's introduce tired light.
Yep.
Well, now we found out why the quasars are as bright as they are. I mean, back in the 1950s and 1960s, 60s is when they first discovered quasars. It's like, these things are very, very bright. And we don't know how to make them that bright.
Yeah.
Well, today we know
we
supermassive
know
black
how to
holes
do
makes
that,
them
right.
that bright. We don't need the tired light. We don't need all these other things.
Well, and that's to your point about, some of the stuff we're finding about these. To me, when I saw, okay, these galaxies are bigger and more complex than we thought. Well, it's like this is the first time where we're seeing the dawn of how all these galaxies formed. I mean, when you go and you don't have actual data, you're going to say, well, here's the simplest model where we get from here to here. And at the minimum, it just says, okay, it's a more complicated model than that. To me, it struck me as we don't understand galaxy formation as well as we thought, which is to your point. Well, we don't understand how quasars could be so bright. Let's keep investigating that.
We're
going to get some good
bright
stuff.
Galaxies, what we really didn't know, how bright are these first stars, how many of them are, how massive they are. We're finally getting some insights into that. And lo and behold, it doesn't challenge the standard Big Bang model.
But I know people were thinking that the first stars were hundreds to thousands times the mass of the sun. The scaling relation we've known for a long time, so they would have put the stars as being that bright and massive. We just didn't have observations to confirm it, though.
Well, it was speculated because people were saying, hey, they're more than 200 times the mass of our star, the sun. Others saying, no, we think it could be down around 10 to 80 times the mass of our star. So this debate's been going on for decades.
Right.
How massive are the first stars? For the first time, we're actually getting some data on how massive these first stars are. And it's actually helping us understand how these early galaxies can be as big and as bright as they are. Also helping us understand how we get supermassive black holes all this early. And I'm basically saying we need to let this play out.
There's an interesting point in there. It's like, for the lack of data, we had to make sure that we include some of those models had these very massive stars, which would have made some of these problems relatively easy to solve.
Right.
Other models said, no, there weren't. For lack of data, all of those models were legitimate. And so in that, finding big galaxies were kind of a subclass, maybe more extreme models, if you will, but they weren't models that it's not that we couldn't explain them. It was just that was not the standard model. That was not the standard picture in our range of models that we had to include. Now, as we get pictures of things, we realize that some of those more extreme models that have always been around are good explanations for it there. It's not like we've come up with a new model. It's like it validates what was maybe a more extreme picture just because of the lack of data.
Right.
Yeah. And science happens that way a lot. So.
Yeah, and then again, going back to the 60s and 70s and 80s, tired light was being invoked by people who wanted to make the universe older. Interestingly, it was also being invoked by young Earth creationists.
I do remember
to
that.
make the universe a lot younger. I'm seeing a revival of that. People are, again, appealing to the tired light hypothesis here, changing laws of physics to make the universe older. I'm also seeing young Earth creationists citing this and saying we can make the universe only thousands of years old. And it's like, wait a minute. We don't just have, the data about the behavior of light. We got cooling curves of white dwarfs. We have radioisotopes that we can look at. There's multiple independent ways for measuring the age of the universe.
Right.
And the challenges of these people trying to make it, say, 26 billion years old, or people making it thousands of years old. Yes, they can look at it to explain some of the data, but not all the data. And so to have a good model, it's got to be, the explanatory power has to be comprehensive. What do you do with the white dwarf cooling sequences?
Well, and I'm going to take a little bit of a different tact on this. I'll just give them the benefit of the doubt that perhaps they can explain all that. Let's just say that's true. I don't know whether it's true or not, but let's just say that's true for now. It does strike me as remarkable. You think, okay, Big Bang cosmology. Yeah, you got dark matter, you got dark energy in there. Those are a little bit of odd phenomena. We're kind of comfortable with them. But given everything it explains, and it's a relatively simple picture, look at what you need to do in order to get a model that might explain everything and be different. You have to invoke tired light, which is arguably one of the most heavily refuted ideas in cosmology.
Right.
And not only that, you have to do that, and you have to make the laws of physics, the physical constants vary throughout the univerce in a way that's almost undetectable.
Yeah, you got to vary all of them.
That kind of puts it shines a light that illuminates just how robust our standard model of cosmology is.
Right.
And all of this, whether this other model is correct at all, still confirms what the scripture said all along. We live in a universe that has a beginning, is reliable, governed by constant law of physics, and points towards a creator.
This is deja vu again for me, because I remember Fritz Zwicky basically saying there's an arcane factor. If the alternative has an arcane feature that's way off scale, that actually shows you that the standard model we think is correct has actually got a lot going for it.
I think this definitely falls in that category.
Okay, very good.
Well, thanks, Hugh. I appreciate the discussion today and hope you've enjoyed our discussion. I want to thank you for joining us, and I encourage you to contribute more in the discussion in the comments below. Remember, like this video and subscribe for more comment. We get new episodes of Star Cells and God released each Wednesday. They're available here on YouTube and on your favorite podcast app. Be sure to share this video with friends and have a good conversation about it. And remember, the more we know about science, the more reasons we have to believe.